Hi, my name is Charles Jochim, and I'm a research staff member at IBM Research in Dublin, Ireland. So I'm going to be talking a little bit about. I know the summit here is about combining behavior science and technology, and so I'm going to be talking about a little bit about how that's being done in the project I'm working on called the Human Behavior Change Project. So I'm going to talk specifically about understanding behavior change through the lens of natural language processing and artificial intelligence, which is what our part of the project is here at IBM Research. First, I guess I should thank Warwick Behavioral Insights teams for this invitation and allowing me to participate in this summit on behavior science and technology. My background is more on the technology side of that with natural language processing and artificial intelligence, and I haven't had the opportunity to speak uh, at all really about our work in behavior sciences. So this is a good opportunity for me, and also the first opportunity that I'm speaking uh, through YouTube. So I hope you will reach out, and any questions that you have or any feedback is more than welcome. The email address is there, or you can really contact anybody in the project. So the project is led by the University of College London, and then we're working on it at IBM Research, and there are members from University of Cambridge and University of Aberdeen. And the whole project is funded then by the Wellcome Trust. So we have a number of members across these different institutions. Uh, I last year, Emma Norris, a member of the project, I think she talked more about HBCP in general, and so if you had a chance to attend last year, I hope you saw her, and she'll have covered it much better than I can. Um, I'm going to talk instead this time more specifically, I guess, about the, the topics of the summit about combining behavior science and technology, and so that will basically, I'm just speaking on behalf of this computer science team from IBM Research. So Paul Mac, uh, Paul Mac Angosa, Francesca Bonin, Debashis Ganguly, Martin Gleitze, Yufang Ho, and Pripalo Tomasi. So yeah, I'll just be covering a lot of the work I've been doing with those guys. First, I guess to put our project into some context, I think AI is an exciting area. And in general, I think it's on a real high at the moment. And NLP, as a part of that, is no exception. Um, After IBM Watson's Jeopardy system, and then later AI systems like DeepMind's Go, and the success AI has had in other areas, it really makes sense that we try to look at how AI can be leveraged for behavioral science as well. Uh, and this is already, I mean, this can be done in different ways. Some in the ways maybe that behavioral science is conducted. If we look at IoT sensors, or how we can measure things, in behavior science, I think it'll change how the science is done. Another area we can look, and I think more in line with what we're doing in HBCP, is how we consume behavior science literature. And when we look at this literature, how we can extract the behavior science knowledge that is encompassed there. And this is, I think, trying to make sense of bodies of literature is done in a number of different domains. And for a lot of the same reasons. One is just the volume of research that's out there. With the volume of existing research, and then how quickly we were publishing and adding to that body of literature, it's just not feasible to do it manually anymore. So we have to use automated ways of processing this. Uh, One of the challenges we have is reporting variability. So as we look across this literature, there are a number of ways that things can be described, and it makes it difficult to synthesize and aggregate over all of that. Context sensitivity is one issue where we, in the behavior change literature, you might want to focus in on a specific context, and look at a specific subset of the literature, and it would be nice to be able to use AI to help with that. And then, of course, I think one of the real advantages of automating this is the timeliness, that you can speed things up so much by using AI and automation. whereas typically the example there is for systematic reviews that might take 2.5 to 6.5 years. By automating some of that, we can speed that up significantly. So that's AI for behavior science more generally. I think for AI, specifically for the Human Behavior Change project, we kind of are looking at NLP and AI solutions to answer questions about behavior change and behavior change interventions. And one of the ways we're looking at this is we consider this big question, which is what works compared with what, how well, with what exposure, with what behaviors, for how long, for whom, in what settings, and why. So this question has been outlined by Mickey et al. in kind of a nice paper that really outlines, I think, the direction that we want to take with our project and kind of what we'd like to accomplish. And for the NLP AI side of that, really what that means is we'd like to do two things, I think. First, we would like to look at different parts of that question, or any variant of that question, really, and be able to extract anything from the literature that we're looking at, perhaps a randomized control trial, extract parts of that question. So maybe the for whom, what populations, or what behaviors, and we'd like to be able to extract that information, one. Then second, once we have information like this extracted, once we know some version of this question, we would like to use inference and prediction to be able to help answer this question, or again, variants of the question. So really find out what works, be able to predict what interventions work, or look at how well kind of try to predict how well they might work in comparison to others. So as I mentioned, there's kind of two things we want to do with the NLP and AI in the project, and the first of those is information extraction. So before we can really extract the information, we need to figure out what are the entities, what is the information we would like to extract. And in this case, we have this inventory of entities that is defined by the Behavior Change Intervention Ontology, the BCIO. And that's an ontology that has been put together over the last year or so, a few years by our project partners at UCL, and they actually it's recently been published, I think, in what's called our Welcome collection, and so you should be able to find details of that on the website, on the Human Behavior Change website. But this ontology defines the entities that we want to extract. And then we're using an NLP approach called named entity recognition, which is a fairly standard task in NLP for extracting entities. So this task is fairly standard in NLP, in natural language processing. But I think the behavior change literature provides some interesting challenges that are kind of unique. And one of them is that the BCIO is actually really is quite large. The inventory of entities is over 500 entities. We're actually only looking at, say, 80 to 90 of these in kind of a prioritized set of entities, but still 80 to 90 is quite a bit larger than what NER systems typically handle, which is, say, on the order of 5 to 10, 15. So we have many more entities, and also these entities are pretty diverse. So one, they can differ quite a bit across behavioral domains, so from, say, smoking to physical activities, but also just within the same domain we find a lot of variety in how, say, income levels or education levels are described, or a number of entities. There's just, our language is so rich, and so why not describe things in lots of different ways, which is great, but it makes it challenging for these information extraction systems. And so when we started the project, starting from scratch, we, in machine learning, kind of in our typical named entity recognition approaches, these approaches are what are called supervised, which means we need a lot of annotated data with the entities labeled by humans, so that our machine learning can learn what these entities look like and where to extract them and how to extract them. And when we started the project, we didn't really have this annotated data available yet. So we took two parallel approaches. The first, to kind of start extracting right away, is that we implemented a rule-based approach which leverages kind of information retrieval type of techniques, a bunch of rules and filters, and using the expert knowledge we have in the domain to extract this information. Then, in the meantime, the team at UCL was annotating this large corpus of. To start out, we're looking at smoking cessation, so this large corpus of smoking cessation reports and RCTs on smoking cessation, and then with this large corpus, we can use our machine learning standard NER approaches. So the rule-based system, basically, you would kind of, for say some BCT like problem solving, we would try to look up text related to problem solving and then apply some rules and filters to find the entities, the BCT we would want to extract, or and so on. I think the machine learning approach that we'll kind of very broadly talk about here learns a lot of the same things that the patterns and rules would, but it's more generalizable, I think, to and it's more scalable as we handle many different types of entities. So we need a large enough corpus, a large enough annotated corpus to be able to really apply this machine learning. And thanks to the team at UCL, we've gotten this type of annotation. So we use a machine learning approach, a little bit more specifically, a deep learning model by LSTM, which is used for named entity recognition. And this identifies some of the same patterns again as our rules does, but hopefully it does a better job. Because one of the things it can do better, for example, is it handles misspellings. It should handle synonyms, abbreviations pretty easily, variations in word order, linguistic variations, so number and verb tense and stuff like that. It handles pretty straightforwardly, and so this makes it pretty robust, where you would, if you want to do this with a rule-based approach, you would need lots of rules to be able to handle all this kind of just slight variation in data. So even with using kind of these state-of-the-art models and having this nice, clean, annotated data, these RCTs still provide plenty of challenges for us. One is that we run into a lot of numbers. These are annotated quite a bit among the entities we have, and we have some trouble with that in kind of disambiguating which entity that a particular number should applies to, and also because a lot of the numbers are found in tables, which is challenging for our modeling. And then again, I think I've mentioned before about how diverse these entities can be, and that is problematic for machine learning models. So now that we have now a system that does a pretty good job of extracting these entities. And so what I guess we should kind of rehash a bit what this can be used for. So one, it's useful on its own. Being able to extract these entities makes it easy to create summaries of the literature. If you're just searching for some specific information in the paper, this type of extraction could be very useful in its own right. But we're also interested in, as I mentioned before, in prediction and inference, and so that's where I'm going to go through a little bit now about how now that we've extracted these entities from the papers, how we can use that for prediction. We can use this inference and prediction. There's a number of questions that we can try to address. So one would be is that if you're given a pair of interventions, which of the two would be more effective? Another could be if you're given a particular context, maybe some population setting, what would be a good intervention to propose? Or maybe you already have like some behavior change, some BCTs in an intervention, but you'd like to add others, how could you complete this particular intervention? Um, or if you have an intervention, if you do change, again, if you maybe change, add a BCT, what might we predict the change in the outcome value to be? And then the last could even be you have all these settings, some set of interventions for a particular population. What would we predict a probable outcome value to be? And so these are all different types of questions I think we can answer with our inference. And when we're looking at that last one, say, what about maybe predicting outcome value? I think thinking of it as a regression is kind of an intuitive way of modeling these outcome values. Um, we found, however, that this was pretty difficult due to the sparsity of the data of the entities we're extracting. They don't all show up in all papers. So because this makes it very sparse in terms of the variables we need for regression, uh, and so it makes this regression pretty difficult to predict this accurately. So going forward, I think we'd like to move from kind of this regression approach to something used more commonly recently in natural language processing, and that's the use of embeddings. So these have become very popular as ways to represent words, and essentially an embedding is this vector representation of a discrete categorical variable. So again, they're used often for words in NLP, where you have this long vector, and any kind of number in the vector doesn't necessarily mean anything in particular, but if you represent that vector in some sort of space, uh, there's nice properties for this kind of richer representation, so that a vector for dog should be fairly close to puppy, and closer to cat than, say, something more distant like blackboard or projector. Um, so these embeddings are really nice for NLP, and we can capture other things with the embedding. So uh, in our case, instead of looking at words specifically, we want an embedding to capture our our entities. In particular, if we as concepts in a graph. So if we build a graph uh, that connects our entities through through links on whether they co-occur in the same papers, we can create a graph on how these entities co-occur, and then we can use a graph embedding approach, something like word2vec, to learn again these rich representations, these embeddings um, for our concepts. So something like problem solving BCT, um, we could learn kind of what it means to be what it means to be this problem solving BCT entity, learned across a bunch of documents instead of just kind of picking out an instance of it in a particular paper, and maybe the context it's in. So um, they can be very powerful tools in NLP. And with this kind of messy graphic, I'll try to explain a little bit of how we use uh, how we can use embeddings. So if you see on the left, we have the documents in our collection, and then we can extract some population BCT outcome values from them, and then put them into this graph. And so the arcs on this graph are how things are connected together. So we have a population here that is connected to this BCT in a paper, so they co-occur in some randomized control trial, and also with an outcome value. And then from this map, we use an embedding algorithm, in our case, Node2vec, and that converts this graph into this embedded representation. And so here on the right, we see that this should be some sort of um, vector space that all these points show up in. And so we could have a bunch of population, all our entities kind of show up in this space with this blue color. Then we come along, we want to find probable outcome values, and so we have a query here of minimum age of 18 and the goal settings BCT, and so we put that query together, and that also is a point in this vector space, and then we look around at things nearest neighbors to this query and identify these outcome values that are similar and will be linked, and then we kind of maybe take an average outcome value then based on those that should be similar, and that could be our outcome value. So this kind of illustrates a little bit of the embedding, the nature of embeddings, but there are some problems with kind of how this nearest neighbor query is done. It's kind of tricky how we'd find that. So really, in practice, we're using neural networks, which is a bit more principled solution for kind of leveraging the power of these embeddings in kind of a state-of-the-art machine learning approach. And one of the advantages of these, so aside from kind of neural networks having a lot of, it's kind of state-of-the-art in natural language processing, one of the advantages here is that we can use the same basic neural network architecture for a number of the predictions that I talked about before. So if we handle it as a regression and want to predict, say, 18.7, this value of maybe the number of participants who have quit smoking, we can use this network architecture to do that. We can also use it for classification. So instead of trying to predict an exact outcome value, if you wanted to predict kind of larger intervals of outcome value, so say low, medium, high, something like that, and turn it into a classification problem, we could reuse this same architecture for that. Or even if we want to say, look at two different interventions and say which is better. So that kind of concludes, I think, what the interesting parts for us as NLP researchers, and I think that covers a lot of what we're looking at in combining behavioral science and technology. But I think one of the interesting outcomes of our project is not just when those two disciplines, kind of combining those two disciplines, the research, but also the behavior scientists and the computer scientists getting together and how we can kind of improve how we work together. And I think that's one of the nice outcomes of the project, and maybe something I should have focused on a little bit more in this presentation. But I think it's really nice looking back on what we've accomplished and seeing. It might be kind of almost cliche, but it boils down a lot to just communication. And I think as we've improved our communication, it improves then the research that we're able to do together. So more specifically on that, I guess, then just a couple points. One is that I think we had to learn not to treat, behavior science AI as some sort of black box. We really needed to understand behavior science a little bit better so that it could help influence our modeling and how we try to answer behavior science questions. Then I think one of the nice things about the project is that we've had a pretty open communication with the annotation team. We meet roughly weekly, and so it was good, kind of initially to understand from them what they would like to extract, what these entities should look like, and then that, once we understood that a little better, it kind of influenced the way we can model those, and then in turn, once we have a better, clearer understanding of how we want to model them, we can inform a little bit the annotation effort and say, okay, well, if you annotate it this way, it should help. It'll be clear for our model. And so again, just along the lines of communication, I think it was good that the behavior science team was good about communicating and helping us along the way as in our understanding of behavior science across different behavior change domains that we were looking at. Although the more we learn, I mean, it's clear we have so much more that we're ignorant about. But it's good. It's good that we're at least starting along that path of learning a bit more about behavioral science. And then in turn, I think we need to do a better job of communicating our NLP and AI approaches to the behavior science team. And I guess this presentation is included in that. So feel free to let me know how I could do a better job of communicating. the NLP AI approaches I've discussed, because I don't. It's hard to find the right level of detail, if it's too much detail or not enough. Um, so I, that's something we need to, from as the NLPers, we need to continue to improve on how we communicate our work, and look for overlaps in how, there's no shortage of behavior science modeling, I think, done, and so we need to look at the overlaps, um, in our approaches, in the behavioral science approaches. So I think I'll close with, this is my last slide. Um, so just to talk a little bit about kind of, I think, the next steps for us in looking at AI for behavioral science, and I think these are actually not really long term. I won't look at kind of long term AI impact on behavioral science, but I think some immediate future is very promising, I think, for AI and behavioral science. So a lot of the stuff coming out of HBCP, I think, already the stuff we're doing, but I think it'll be improved in the next, in the years to come, would be how we search and retrieve information from the behavioral science literature. And then along with that, some of the stuff we've already talked about, and kind of the automatic, or semi-automatic synthesis of this literature. And that kind of goes hand in hand with automating parts of systematic reviews, and this is already being done, I think, by other groups. But I think if we can, improve this automatic synthesis, it will really go a long way in kind of speeding up, the systematic review process. Then, as I mentioned at the beginning, I think already there are changes in kind of how we observe and measure behavior change, with IoT sensors and other all kinds of devices. So I think in the near future, as this data becomes ever more prevalent, we have more and more sensors, and as this data hopefully will be kind of the way it's reported is standardized, I think the different types of machine learning that we'll be able to apply, and as this data increases, um, we'll be able to do a lot more intelligent kind of analytics on that, and this will lead to better and better insights. And again, the promise with all this kind of automation is that it's quicker and quicker to do this. So yeah, I'll close there. Thank you. Thanks very much for the attention, for sticking with me this long. Thanks again to the Warwick Behavioral Insights team for the invitation, and for allowing me to be a part of this summit. And yeah, please reach out if you have any questions about the project. My email address is there, or anybody in the project. We'd be happy to discuss the project or behavior change, the ontology, any parts of the AI process that I've described here. It'd be great to get your feedback. Thanks very much.